Part one of the midterm review, just showing you how to do some of the problems that we got on here. Um, so again, let me scroll down to where kind of our first problems are. A couple things in here on empirical formula. So as a reminder, empirical formula is us trying to say what is the composition of a compound in its simplest parts. So number one is asking for an empirical formula. That means that our answer needs to have lithium, carbon, and oxygen in it. Kind of our process is to go from percent to grams to moles to get a ratio. This one starts with percent, so just to keep it kind of moving along, I'm going to go ahead and put the grams on here. So I got lithium, carbon, and oxygen. So if I take my numbers and convert them into a gram, I don't need to do anything other than put a G at the end of it. So then our next step is to change this to moles, which means I need to divide by the molar mass of each one. I've already worked these out over here, so I'm looking over to the side. Got these from the periodic table. So lithium 6.94, carbon 12.01, oxygen is 16. All right, so when we get this is going to tell us how many moles are in each one. And I'm not rounding these numbers very well purposely. So 26945, carbon 1.3572, oxygen 4.0625. And so this is the number, this is the moles in each one. But again, these numbers are kind of hard to see. So what we want to do is to divide each of these by the smallest of the terms to basically translate the ratio. So the smallest of these is 1.35. If I divide each of these by 1.3572, it's going to make my numbers look a little bit different, but it's the same ratio. So I'm basically dividing them all by the same thing. And the top number ends up being 1.98, which effectively is 2. The middle number divided by itself is 1. And the bottom number is 2.99, which effectively is 3. These are the numbers that go into my ratio. So in other words, there are 2 lithiums, there is 1 carbon, and there are 3 oxygens. So the formula is Li2 carbon O3 that we have there. So again, there's twice the number of lithiums as oxygens. And if you look at these numbers, that kind of makes sense. 2.6 is basically twice of 1.3. 4.0 is basically 3 times the size of 1.3. And so the ratio part just kind of cleans this up so it's a little bit easier to see. That should be our answer, Li2CO3 on that one. Let's scroll down to number 2, which is the same kind of question, a little quicker to do this one because there's not as many elements and it's not in percentages. So I've got 36 grams of carbon and 114 grams of fluorine. I'll start with a C, start with an F. I've got 36 grams. I've got 114 grams. I'm going to divide by the molar mass. For carbon, it's 12.01. For fluorine, it's 19. This would tell me how many moles I've got. And then if we divide these by the smaller of the 2 numbers, then I can translate this into something that's a little bit simpler for easier to see. That becomes a 1, that becomes a 2. And so that tells me my ratio. I've got 1 carbon and I've got 2 fluorines. That's my final answer. All right, a molecular formula is the actual honest to goodness formula. This is one of the things we didn't really go over in much detail, but all we need to understand is that the molecular formula is generally going to be a multiple of the empirical formula, which means the mass is also going to be a multiple. So this one says the empirical formula is P2O5. All right, and we're trying to find out what is the molecular formula, which would be a P and an O. And again, these numbers are going to be in multiples of 2 and 5. So it's going to be 2 and 5, it could be 4 and 10, it could be 6 and 15. It says experimentation shows that the molar mass of the compound is 283.89. Now, if I take the molar mass of this, if two phosphorus and 5 oxygens, and put all of that together, and I do the math for it, using the periodic table, this should weigh 141.94. All right, so again, this weighs 141.94. This weighs 283.89. I can basically set up a ratio. In other words, how much bigger is this number than that number? So if I put my final number on top of the bottom number, this basically ends up being a 2. In other words, this number is twice as big as this number, which means that my subscripts in the molecular formula need to be twice as big as the subscripts over here. So my 2 and 5 are going to double, and it's going to double into 4 and 10. So this would be the molecular formula, and if you did the math, you could verify that that actually weighs 283.89. So when we don't know the molecular formula, what we can do is figure out the ratio of weights. How much bigger is the molecular formula compared to the empirical, and then use that number to be able to multiply. Similarly, on number 4, if we wanted to find the molecular formula, 1 nitrogen and 1 oxygen, so the empirical formula is NO and has a molar mass of 60.01. So again, I've got an N and I've got an O, and it weighs 60.01. If I add up the nitrogen and the oxygen on the periodic table, that's going to give me 30.01. Right. So if I set up a ratio, the weight of the molecular formula divided by the weight of the empirical formula, that's again going to come out to be 2. So in other words, this number is twice as big as this number, which means I need to basically double my formula. So everything in the formula gets doubled, which makes it nice and easy. So when we're done with this, my formula should be N2O2 to finish that one up. All right, molar mass, again, we're just looking on the periodic table. What we need to do with this one is carbon is 12.01. There's 6 of them. Hydrogen is 1.01. There's 12 of them. Oxygen is 16. There's 6 of them. We need to take all of these numbers and we just sum them up. So the entire weight of this, when we get them all done, should be 180.18. So molar mass is something we've been doing for a long time now. So 1 mole of glucose is 180.18. If we're going back to asking how many atoms are in something, this is where we get back with Avogadro's number. Avogadro's number, again, is 6.02 times 10 to the 23rd. So this is how many atoms are in 1 mole, or how many molecules are in 1 mole. But again, this is the number of particles in 1 mole. So if I have 3.14 moles and I want to know how many atoms I've got, again, each water molecule has only 1 atom of oxygen. So if I know how many waters I've got, I also know how many oxygens I've got. So basically, I just need to take 3.14, and I'm going to multiply that times Avogadro's number, because this is how many molecules are in 1 mole. This was 3.14 moles. So the moles are going to cancel out. 3.14 times 6.02 times 10 to the 23rd. My math ends up giving me 1.89 times 10 to the 24th. Remember, in your calculator, we're not ever putting times 10 in the calculator, so let's don't do that. We need to hit the second E button so that that's what shows up on your calculator when you do that. So make sure you're rounding your answers correctly, estimating correctly. So that's how we get our answer for number 6. 7 is how many moles are in grams. So this is just a gram to mole conversion. If we know that we've got 1,000 grams and we want to change that to moles, then we just need to know the ratio here. So 1 mole is, again, 58.44 grams. I got that from the periodic table for NaCl. So if I take 1,000 and divide it by 58.44, that should give us our answer, which is going to be about 17.11 or 17.1 moles of NaCl. All right, number 8, how many atoms are in 33 grams of sulfur? If I need to go from grams to atoms, I've got a couple of steps I need to be able to take here. So I need to go from 33 grams of sulfur. I can't turn grams into atoms, but I can turn grams into moles. And then I can turn moles of sulfur into atoms of sulfur by Avogadro's number. So to turn grams into moles, I need to say if I have 1 mole, how many grams would that be? I get that again on the periodic table. The molar mass of sulfur is 32.7. And if I need to change my moles into atoms, then I need Avogadro's number, because 1 mole is going to have 6.02 times 10 to the 23rd atoms in it. So I'm going to take 33, I'm going to divide it by 32.07, I'm going to multiply it by 6.02 times 10 to the 23rd, and I'm going to get approximately 6.19 times 10 to the 23rd atoms. Scroll down for a couple more here. Should have enough time before I get interrupted again. On number 9, I got 2.01 moles, and it's asking how much Fe. I'm going to assume that that is in grams. So this is a mole to gram question. So I need 2.01 moles of Fe2O3. I got to put this on the bottom to cancel it out. I'm going to turn moles of Fe2O3 into moles of iron. And then I need to turn moles of iron into my final answer, which is grams of iron. Moles over mole, this is our molar ratio. This is where we need to get our numbers from the periodic table. There's a 4 in front of the Fe. There is a 2 in front of the Fe2O3. So I got 4 over 2 because I need twice as many moles of iron as I have iron oxide. This is my molar mass, molar ratio. So molar mass. So 1 mole is going to be 55.85 grams. I get this again from the periodic table. So in my calculator, 2.01 times 4 divided by 2 times 55.85, and that should give me 224.5 grams. Right. And one last one before I pause the video and make a second one. Number 10 saying how many grams of magnesium are used if the experiment requires 2.53 moles. Again, same kind of question. If I've got 2.53 moles of magnesium oxide, so I need to cancel out the moles of magnesium oxide, and I need to change that to moles of magnesium. And then I'm going to need to cancel the moles of magnesium out and change it into grams of magnesium. So my first set of numbers to get is the molar ratio between magnesium and magnesium oxide. That's coming from a balanced chemical equation. There's a 2 in front of the magnesium. There's a 2 in front of the magnesium oxide. Basically, those are going to cancel each other out. Over here, this is our molar mass. Molar mass always has a 1 in front of the moles. And for the magnesium, I'm getting that from the periodic table. And I'm going to get 24.31 grams. So in calculator, 2.53 times 2 divided by 2 times 24.31, and it should give me 61.5 grams. All right.